So this is going to be a review of Domain 5, Enterprise Security Architecture. We're going to quickly review all the major components of Domain 5. Let's start with hardware. We're going to start with the CPU and the arithmetic logic unit that is the core of the central processing unit. So the ALU is the center of the CPU. The control unit is a component, also a part of the system, that aligns instructions and data and coordinates its flow into and out of the CPU. We have primary memory, which is buffer memory or registers that live on the CPU substrate. And what the control unit is aligning in those buffers is the thread or the instruction that goes into the CPU, and then data. And then it channels that information into the CPU for processing. We have level 1 cache and level 2 cache. Level 1 cache lives on the CPU substrate. Level 2 cache is very close electrically and physically to the CPU chip itself. Further away regarding memory, we have random access memory, or RAM. RAM is a major component of the system. The more RAM we have in the system, generally speaking, the better performing the system performs. We have the address bus and the data bus. These are parallel wires. The more lines we have in the address bus and the data bus, the better performing the motherboard. These are components that live on the motherboard themselves. We have the memory manager. Now this is an operating system executive service. The memory manager provides abstraction between the user level, the application, and the actual physical memory. The memory manager has a subcomponent called the virtual memory manager that provides paging to a page file that simulates virtual memory, simulates RAM for the computer system. But remember, virtual memory is approximately 1 million times slower than true physical RAM. We have the hard drive that operates at about 10 milliseconds, whereas RAM operates at about 10 nanoseconds, 10 nanoseconds being 10 over 1 billionth of a second. And hard drive operates at about 10 milliseconds in access time. That's 10 over 1,000th of a second, so it's 1 million times slower. We have optical drives such as CD-ROM and DVDs. These devices typically run in the range of 100 to 250 milliseconds access time, so they're even slower than the hard drives. Then we have tape drives, which also provide a linear read. These are linearly written onto tape. We have applications that spawn multiple processes, and those multiple processes can spawn multiple threads. The thread being the instruction that the control unit controls in the buffer memory and feeds into the CPU. So the thread is the instruction that the CPU can understand. As we launch applications, they spawn processes. Those processes are assigned resources. These resources are protected, and one of the major components of resources that the process is allocated is something called the stack. The stack is a region of memory that is assigned to the process and then is protected for that process. Now we're going to move into operating system protection mechanisms. We're going to talk about kernel mode versus user mode. Kernel mode is also referred to as privileged mode or supervisor mode, and it is the most trusted execution mode in the system. We have user mode that is also referred to as problem mode. This is a less trusted component in the system. We have the memory manager, and we have a security kernel. These are executive services that are assisting the kernel in the performance of the operating system. We have memory with physical segmentation. We also have logical segmentation for memory. Physical segmentation is where we will allocate processes and data to a single RAM chip, versus logical segmentation is what the memory manager does as it assigns virtual address space to an application, but then maps that behind the scenes to actual physical or absolute addressing in true physical RAM. We have process isolation. Again, this is a logical segmentation for processes. This isolation is also referred to as layering, data hiding, abstraction, and black boxing. These are all isolation mechanisms that provide security for the processes and data that is being manipulated and stored on the computer system. We have virtual machines, again a layering or isolation technology. We also have the protection ring architecture that is supported by the hardware, but it is implemented by the operating system. And in the Microsoft operating system, they use a 4-ring system, with ring 0 being where the kernel lives, the most trusted component, and then ring 3, the least trusted component, is where the user lives and all the user applications live. Again, we have the execution domains that are either user mode or kernel mode, and this is identified by a flag in the stack called the program status word. Again, this is stored in the stack, and it identifies whether this particular process is to be run in user execution mode or kernel execution mode. The security domain is a definition. The definition of this is the collection of all objects that a subject has access to. It is also referred to as the user's profile, the user's capability, the user's level of privilege. We also need to remember that of all the input and output devices, we must ensure a trusted path between those devices and the actual execution in the CPU. Next, we're going to look at the enterprise security architecture. This is the implementation of security as our computer systems store, secure, and process our data. It starts with what's called the trust hierarchy. The user trusts the application trusts the operating system, and the operating system trusts the hardware. The user, of course, is the least trusted entity on the system, and the hardware, of course, is the most trusted entity on the computer system. We also need to recall that we can be compromised from above. That's an unauthorized user modifying data or manipulating data. From within, this would be a virus or microcode. The compromise from within is an authorized user making unauthorized modifications, and then compromise from below would be a virus infection in the source code or microcode. Enterprise security architecture also deals with the trusted computing base. And remember, the intention of the TCB is that it is designed so that the government can acquire computers that can be trusted to preserve the confidentiality of our valuable information assets. This is based all upon the Bell-LaPadula confidentiality model. The trusted computing base is defined by the Orange Book, which was developed by the National Computer Security Center, or NCSC. This further goes to define how a computer can be designed, manufactured, delivered, and installed and remain secure through that process, so that we can now trust that this is a trusted computing base, and the processes we add on top of this can be at least as secure as that system. The TCB includes the hardware, the firmware, the microcode, and the operating system, but does not include security of the applications. The TCB defines a trusted computing base perimeter. This is a well-defined boundary between what has been designed, manufactured, delivered, and installed securely, as well as being certified that it's been implemented securely, versus outside the perimeter or components that have not achieved this level of certification. We have 4 main functions for the execution of processes. We have process activation. We have the execution domain switching as we toggle from user mode to kernel mode using the program status word. This is a second of the 4 main functions as we are executing our processes. Further, we have memory protection, and then we have I/O operations that must also be ensured as trusted. Remember, the trusted path of my input and output components. We also need to remember that we have a security kernel that implements a component called the security reference monitor. This reference monitor is a boundary between the subject and the object. The security reference monitor has 3 main requirements that must be implemented in order to satisfy the trusted computing base. The first rule of the security reference monitor is it must provide isolation and be tamper-proof. The second rule says it must be invoked 100% of the time and cannot be circumvented. And the third rule says it must be small enough to be tested and verified in a cohesive manner. In addition to all these, to ensure enterprise security, the system must also provide self-protection. It has to have trusted recovery mechanisms and self-protection mechanisms built into it. Next, we're going to look at access control models. First, we're going to talk about discretionary access control, which is a model that utilizes an access control matrix. Now, discretionary access control, or DAC, is used in the commercial world, and it uses access control lists. It is the weaker of the access control models, but it is affordable. In the access control matrix, we have a subject that is defined, that defines a capability. So the row in the access control matrix is called the subject's capability. The capability is bound to the subject. The column in the access control matrix is referred to as the ACL, and the ACL is bound to the object. And the weakness of the discretionary access control model is that subjects can transfer privilege. If I grant a subject the read permission on a file, that subject can read and then save a copy of that file. Being the owner of that new copy, the subject can now grant whatever level of privilege on his copy of that file he chooses to. This is the weakness of DAC. Now, the second access control model is mandatory access control. This is the stronger, more rigid access control model. It uses a lattice structure, and this defines layers. The strength and the cost, high cost of mandatory access control models, leaves it only for use in the military and government sectors, because they're the only ones that can afford and need this highest and most rigid level of security. It defines a subject that has a clearance and a need to know. These are labels that get assigned to a subject. It also then defines objects have a classification and a category. These are two labels assigned to the object. When the subject's clearance and need to know aligns with the object's classification and category, the information can be accessed. The object can be accessed and information can flow. The strength of the mandatory access control model is that subjects cannot transfer privilege as they could in the discretionary access control model. Mandatory access control models have 4 modes of operation. The first mode is called dedicated security mode, where all data is at the same security level and all subjects can access 100% of the data on the system. The second mode is called system high security mode, where we have data at different security levels. User can access data based on the user's need to know. The third mode is called compartmented security mode, where we have data at different security levels and the user can access data based on the need to know and a formal access approval. And the fourth mode in mandatory access control is called multi-level security mode, where we have data at different security levels and a user's access is based on their need to know, formal access approval, and a clearance. In enterprise security architecture, all mechanisms must align to meet the security needs. The security program is designed and implemented and has many, many layers. Processes are infused with security, and we must evaluate the effectiveness of our security mechanisms. This requires monitoring and auditing. Next, we're going to take a quick look at the formal mathematical academic security models. These are the foundation of the implementation of security mechanisms in our information system. The first model is the state machine. The state machine pretty much says no matter what happens to this system, no matter what state it is in, the system will remain secure. The second model is called the information flow model. The information flow model basically says no matter how the information flows from one state to another, it will also remain secure while it is in transit. There are 4 ways that information can flow within a system: from input to output, from input to the next state, from one state to the next state, and from one state to output. The next model we'll talk about is called Bell-LaPadula. Bell-LaPadula is a confidentiality model based on mandatory access control, or lattice. Lattice also implies labels used in military and government. Some basic rules of Bell-LaPadula. The simple principle says to protect confidentiality, if you are at a layer in the in the lattice, you are not allowed to read information at a higher layer. The simple property says no read up. The star property says no write down. Again, to protect confidentiality of information, you are not allowed to write data to a lower layer. Otherwise, you are divulging secrets. The strong star property says you are constrained by the single layer at which you are assigned. You cannot read up or read down. You cannot write up or write down. Further, the Bell-LaPadula model also identifies something called the tranquility principle. The tranquility principle identifies a resistance to change the labels once they've been assigned. That is, clearance, classification, need to know, and category. Once these labels are assigned, there is a tremendous resistance to change. That is called the tranquility principle. BIBA is the next model we'll talk about. BIBA is an integrity model based on mandatory access control, lattice, labels, military government, strong, expensive, etc., etc. BIBA also has three properties we need to deal with. First is called the star axiom. Star axiom says to protect the integrity of data, subject at a lower layer cannot write to a higher layer. No write up to protect the integrity of the information at the higher layer. The simple axiom says no read down. To protect the integrity of information at your layer, you cannot pollute your data with less level of integrity by reading data from a lower layer. So no read down. The BIBA model also identifies a property called the invocation property, which says a subject cannot make requests of subjects at a higher layer. That would be a subject saying, can you modify that record for me up there? And effectively, we are polluting the integrity of the information at the higher layer. So the invocation property says no requests are allowed to be made at to a higher layer. The next model we're going to look at is called the Clark-Wilson model. Clark-Wilson model is an integrity model used in the commercial world. It is defined by well-formed transactions, separation of duties, and auditing. Again, it's an integrity model used in the commercial world. It defines an access triple that recognizes that users use programs to access and modify data. So the three components in the access triple are user, program, and data. There are also three integrity goals related to the Clark-Wilson model. The three integrity goals say no unauthorized user can modify data. The second rule says we must provide for internal and external consistency. And the third rule says authorized users cannot make improper modifications. If we satisfy these three things, we improve the integrity of the information in our commercial arena. Next, we're going to talk about the non-interference model. The non-interference model defines a security domain. Remember, the security domain is the collection of all objects that a subject has access to. The non-interference model says users' actions in one domain cannot affect or interfere with users in another domain. So basically this says what you're doing in your world cannot affect the integrity and the confidentiality of the information in my world. The next model we'll talk about is called the Brewer-Nash model. The Brewer-Nash model is an integrity model implemented for the commercial world. This model is context dependent, and it is designed to prevent a conflict of interest. The Brewer-Nash model is also referred to as the Chinese wall, where it dynamically assembles ACLs based on prior access to isolate the subject from accessing other content. Once you touch one piece of data, you are no longer allowed to touch any other piece of data. So it is context dependent. The next model we'll talk about is called the grant-take or take-grant. This is basically a testing methodology used for granting and revoking permissions in security systems. So we're going to grant and then revoke permissions and evaluate the outcome to ensure that we get exactly what we were desiring. The next model is called Graham-Denning. Graham-Denning is a model that defines how we are going to manage our subjects, manage our objects, and how we are going to manage the granting and revoking of privileges. And finally, the last section in this review is going to deal with the evaluation assurance criteria and ratings. This started with a TICSEC that was developed in 1983 by the National Computer Security Center and the NSA. It was based on Bell-LaPadula, and the outcome of the TICSEC is the Orange Book that defines the Trusted Computing Based, or the TCB. Now, the Orange Book defines security on a standalone system. There is also a Red Book that defines what's called the Trusted Network Interpretation, or TNI. These are 2 books out of the Rainbow series. The Rainbow series has a total of 26 books in the collection. The TICSEC defines several levels of security, going from D being the minimal level of security to level C, which defines discretionary access controls, to level B, which defines mandatory access controls, to level A, which defines a formal verification of security mechanisms. Formal verification typically implies mathematical proofs, academic mathematical proofs, to validate the effectiveness of the security for the system. Now, this was improved upon by the ITSEC, that is the European enhancement to the TICSEC. This was introduced in 1993. It extended the range of the scale from 0 to 10 and also broke functionality from assurance. Remember, functionality says I can do it at least once. Assurance says I can do it every time. So the ITSEC was an extension of the TICSEC, again, based on the academic model of Bell LaPadula. That was its weakness, is that it was based on this academic model and not based on real-world need. So the ISO developed the common criteria in 1993 that identified real-world security needs. The common criteria was implemented in ISO standard 15408, and it identifies 7 different protection profiles, or levels of security needs based on real-world need. These protection profiles basically define what's called the evaluation assurance levels, or EALs. So the government specifies 7 different levels of security, and then will specify I need to buy, for example, 10,000 computers at EAL level 4. They submit this request to vendors who are going to produce this hardware. The vendor then identifies a target of evaluation, or a TOE, often called the TOE. The target of evaluation is the vendor's product that hopefully will satisfy the protection profile. The vendor also produces something called a security target. This is a write-up on how the target of evaluation will satisfy the protection profile that is desired. Now, the vendor will then take the target of evaluation, the security target, and a big fat check and send it to an accredited testing center. The testing center has been accredited by the U.S. government, and the accreditation identifies this testing center will correctly and accurately and unbiasedly evaluate the target of evaluation and certify that it either meets or does not meet the protection profile required. Again, there are 7 levels in the EAL scale. We have EAL 1 that identifies functionally tested, all the way up to EAL 7 where it's formally tested, and then of course the levels in between. Once a system has been certified as an EAL level 4 device, it goes on what's called the EPL, the Evaluated Product List. So now the government can simply select that target of evaluation that has been certified at a specific EAL level and can purchase them directly. Certification says the device has been tested and it meets its requirements. Accreditation is the government's trust in the testing center. The government says if they've tested it and certified it, then it must be good. This has been the review for Domain 5, Enterprise Security Architecture.